Hello and welcome. This is the Chapter 3 summary video. So I thought we'd get to start with this video with the problem from lecture, which is talking about the number of molecules of N2. So we have 10 molecules of N2, 24 molecules of H2. They're reacting to form NH3 by the reaction noted here. So it's 1 to 3, making 2 NH3s. So how many molecules of NH3 form, and which reactant remains as the excess reactant? So what this is maybe going to try to help us figure out is how to think of like a before and after. So if we picture a before, the reaction takes place. You know, we can sketch these. So we have an N2, another N2. So I'm going to draw 10 of these. So that's 3, 5, 6, 7, 8, 9, and then 10. And then H2s we can draw in. So I'll need 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2. So that's 3. That's a 4. 4. I keep drawing errands. Dang it. So we'll draw an H. H2. H2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6 H2s. Okay, so we should be able to sketch a picture out of this if we want to. So let me lasso out. It's blue here. So if I lasso these out, I got 3 H2s and an N2 in the middle, the right ratio, and then after the reaction takes place, what I should end up with is 2 NH3s. So I can do it again. Let me take 1 N2, and we get 3 H2s. So I got another 2. So we can always make a picture if we have to. There's no reason why we can't just make a picture if that helps us solve the problem. We're just trying to picture, you know, how many of these we're going to get. So I'm up to 8, 9 and 10, 11 and 12. So got an N2 here. Might have to lasso a few H2s. Let me do this one here. That gets me 3 H2s, another N2, so another NH3, NH3, and then look here, we got 3 N2s left, but only 3 H2s. So I'm going to take the middle N2 plus this one plus that H2, and so I'm left behind. I don't have too many colors left. I got green N2s left behind, and I got to sketch in my 2 NH3s. So these are my 2 final NH3s that are made, and then I have my final 2 N2s that are left over. So we can use the lassoing technique if you will. Draw a picture, think about what's present before the reaction, start thinking about making the products, and then you're going to be left after the reaction with your products plus any of the excess reactants. So the excess reactant is N2. 2 molecules remain of the N2. And then we had reacted 8 of the N2s, and then we had produced, if we count up the NH3s, we had made 16 NH3s. So 16 NH3s are made, 2 molecules of N2 remains following the reaction. Okay, so let's look at the problem again. One of the beauties of stoichiometry is you can solve these problems a variety of ways, and all of these ways really should make sense. The next approach that I'm going to show is, well, let's make a BCA chart. So let's imagine we have N2 plus 3H2 goes to 2 NH3. Initially, we don't have any of the product. When we have 10 molecules, I'm going to use a molecule with the C symbol here. Then I have 24 molecules of H2. Okay, now a few ways that we can think of our change here is that we could either do a minus x, minus 3x, and a plus 2x. That might help us. And then one of the keys is after the reaction, one or both of these should go to 0. So the question is, which one? And so what you might do is think, okay, let me just randomly choose one. We can pretend like we didn't do this problem already in the previous slide, and like let's assume N2 goes to 0. So if N2 goes to 0, then X is equal to 10 molecules of N2, and then for every 1 molecule of N2 that reacts, we have to react with it 3 molecules of H2, so we have to have 30. So if you think of this loss here, if we take N2 to 0, we would have to lose 30 molecules of H2, but we don't have that quantity. This would be minus 6 molecules. So we can't go negative, so that's impossible. So what you might do is say, okay, then the other has to be true. The other reactant must be true, that we take H2 to 0. If that's the case, then X must equal 8 molecules, or let's just say X is equal to 8. So then 3 times 8 is 24, so we lose all 24 molecules of H2. Therefore, we only lose 8 molecules of N2. We're left behind with 2 molecules of H2. And then we produce 2 times 8, so we end up with 16 molecules of our product. So here's our 16 molecules of NH3 and our 2 molecules of N2 that are remaining after the reaction. So we can set up and use a BCA chart if we find that to be useful for this type of problem. Okay, let's do it again. Let's think through another way to solve this problem. So another way to solve this problem might be to, I'm going to write the reaction just so I can have it in larger font, easier to point to. So I'm rewriting the reaction. So now what I might do is just think in terms of like solving this like a stoichiometry problem. So I might say, okay, how many molecules of NH3 can I make if I were to consume all 10 molecules of the N2? And if I did so, for every 1 molecule of N2 that reacts, we would produce 2 molecules of NH3. So if we could run this reaction here, we'd end up with 20 molecules of NH3 produced by this reaction. Now I can run this again. Like if I'm just kind of randomly choosing all of one of the reactants here, I need to run this through a second time here with the other reactant to see if I'm going to make more or less than this quantity. So let's just run through it and then talk about what we can learn from this second problem. So we're doing this with the other reactant. So the other reactant's H2, 24 molecules initially present. We take for every 3 molecules the H2 that react, we produce 2 molecules of our product, still using the 2 to 3 from our reaction. And so that's going to give us 16 molecules of NH3 produced. So once I hit 16 molecules of NH3 being produced, this H2 has gone down to 0. And if I were to go to 20, I'd need more H2, so I can't go to 20. So this is an impossible quantity to make, given that once I hit 16, that's going to be the maximum the yield can be on NH3, so that would be 16 molecules. And so then we might then say, okay, now that we identify H2 as our limiting reactant, it's one completely consumed in the reaction, the number of molecules of N2 that are reacted with this quantity, we can use stoichiometry to say, okay, we got 24 molecules of H2 that react. For every 3 molecules of H2 that react, 1 molecule of N2 reacts with it. So this should be a molecule of N2. And this is H2 here. So 3 molecules of H2 react with every 1 molecule of N2. So that's 8 molecules of N2 react. And then I can remember or just know that, well, if I have 10 molecules initially, without a BCA chart, I should be able to just simply subtract the 8 molecules that react and left behind with the 2 molecules of N2 that remain. So we can apply some thought and use a dimensional analysis string to solve these problems as well. So we have make a picture, use a BCA chart, or use dimensional analysis as our key problem-solving techniques. Okay, one last way we might think through this problem here is to think about the ratios or the coefficients in the reaction as a way to help us solve this problem. So I might be able to identify the limiting reactant just by thinking about the relative amount of N2 to H2 compared to the coefficients. Like I need 1 N2 for every 3 H2s, and I clearly have less H2 than a 1 to 3 ratio. If I had a greater than a 1 to 3 ratio of H2, then I'd consume all the N2 in the reaction and be left behind with some of the H2. So I think we can identify the H2 as a limiting reactant if we just think of the relative amounts of N2 and H2 that we have given to us here compared to the ratios we need to react according to the reaction. And so I think we can identify H2 as a limiting reactant, therefore easily identify N2 as the excess reactant, and that by a 1:3 ratio, we're only going to react 8 of the molecules of N2, so we'll have 2 molecules of N2 left over, and then for each 3 of the H2s that react, we get 2 NH3s as a result, so therefore we're going to end up with 16 molecules of NH3. I think in order to look at the problem this way, you have to have a pretty good understanding of a particle diagram. Maybe the first method has to make sense to us. Thinking through a BCA chart, I think, is kind of important because that's what we're thinking about when the reaction takes place. We're thinking about the one reactant losing X for 3X of H2, and then we're gaining 2X in terms of NH3. Like, we're picturing that, whether we're solving it with a BCA chart or dimensional analysis or just through thought analogies, we can arrive at the same answer. So there's a few different ways we might approach this problem, but I think to get one of them, you have to get all the methods, or at least to get the last one where we're kind of hand waving and thinking through this just in terms of ratios. We have to have a pretty good understanding of stoichiometry and particle diagrams and BCA charts, because we're really thinking about all that as we are doing this thought. Okay, so let's come back and review combination reactions where we're putting 2 or more substances together, forming a product. So taking nonmetals together to form molecular compounds like CO, or forming ammonia. We could also have the idea of adding calcium oxide to water to make calcium hydroxide is another example. So anytime we have 2 or more substances adding together for a single product, that's a combination reaction. We did see the general case of a metal, say calcium, plus a nonmetal, plus chlorine react to form an ionic compound, like CaCl2, where we're making the ionic compound. This would actually be balanced as written, so we can have a metal plus a nonmetal forms an IC, an ionic compound, as a general type of a combination reaction. So decomposition reactions are where one substance breaks down into 2 or more. So a general formula here is a C goes back to A plus B. So the examples that are shown here are chlorates sort of losing oxygen and forming chlorides. We have the carbonates, we saw this example in class, losing CO2 as a gas and forming the oxide. Then we also have hydroxides forming an oxide and losing water. So you really don't have to have these memorized per se, other than maybe the carbonates losing CO2 upon heating is just a general type reaction that we noted in our lecture notes for this type of reaction. So this decomposition, calcium carbonate loses CO2 upon heating. You can extend this to other types of cations. We're not changing this charge state of the metal, so we're keeping the metal at the same oxidation state it's in. Carbonate's charge is a 2-, oxide's charge is the ordinary 2-, so we're just losing a molecule of CO2 off the formula through heating. So combustion reactions occur when C and H compounds are combusted in the presence of oxygen to form CO2 and water. We mentioned that if you don't have enough oxygen for this reaction, ordinarily reactions just turn off and don't produce as much products, and you're left with one of the other reactants as your excess. This can actually change, the chemistry changes. If we don't have enough oxygen, we're going to make carbon monoxide instead of carbon dioxide. And of course, this is a deadly poisonous gas. So this is just a reminder, make sure you have your vents cleared, maybe a clean filter put into place in your furnace if you have a natural gas or propane furnace as we approach heating season in the winter, because if you don't have enough oxygen, you're going to make a deadly poisonous gas, and of course it doesn't smell, so you will not notice the odor. So formula weight is the sum of the atomic weights for the atoms in the chemical formula. So, and we can think of something like H2SO4 as a molecule. So it has a formula weight which is synonymous with its molecular weight, which would equal the 2 H's plus the S plus the 4 O's. So we'd have 1.008 times 2 plus 16.00 times 4 plus 32.06, and whatever that totals up to would be the atomic weight for the compound. So the significant digits we should be using here, I like to use at least 4 sig figs on my atomic weights. That's usually enough for most of the problems I'm going to see. So if I work this out for the molecule, it's 98.08 AMU. So we're tracking these units on the periodic table in the atomic mass unit scale, we saw in class that this would also be synonymous with the mass of 98.08 grams per mole, and that this AMU mass is for one single molecule of H2SO4. So the mass of one molecule of H2SO4, 98.08 AMU. The mass of a mole of H2SO4, 98.08 grams. We can define the percent composition of an element by taking the number of the atoms in the formula for the atom times the number of atoms. Actually, one of these should be the atomic weight of the atom. So the number of the atoms in the formula times the atomic weight of the element, and then divide by the formula weight of the compound. So the percent of carbon and glucose, I don't expect you to have glucose memorized. Most of us probably know it's C6H12O6. So you don't necessarily need to have this memorized, but the percent carbon would just be equal to 6 carbons times 12.01 AMU for each of them, and then divide by the formula weight of C6H12O6. And so that's about 180.2 AMU if you put together all of the 6 times carbon, 12 times H, etc., times 100%. And so that would work out to 6 times 12.01 divided by 180.2, works out to about 39.99%. So about 40% of the mass in glucose is due to the carbon atoms. So Avogadro's number, 1 mole is defined as an Avogadro's number of particles. So 1 mole of X is equal to this number of particles of whatever that X happens to be. And so this was previously known as the measured number of atoms in a carbon-12 sample. It is now taken as an actual given, that this is just what it means to have a mole of a substance by the current definition set forth by the IUPAC, the International Union of Pure and Applied Chemists. So therefore, there's an Avogadro's number of carbon atoms in a sample that has a mass of 12 grams, and that would be a mass that's 12.00 out to a bunch of zeros grams. So I think it's 9 total placeholders. So 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. So we need one more zero. And so each atom has a mass of 12 grams. This is kind of like an exact mass, if you will, or a number that used to be considered exact. So it's a nearly exact number. Divide by Avogadro's number. Gives us 1.993 ... times 10 to the minus 23 grams. Okay, so each carbon atom has this particular mass of grams. So in the AMU scale, the way the AMU scale is defined is by taking 12 AMU as the mass of carbon in the AMU scale and setting it equal to its actual mass, 1.993 times 10 to the minus 23. I'm going to keep all those digits here so I can get my conversion to AMU. I'm going to divide my AMU for one carbon atom by 12, which tells me that so 12 AMU is equal to 1.993 times 10 to the minus 24 grams. So 1 AMU, divide both sides here by 12. So 1 AMU is therefore equal to 1.66054. You can keep going out, times 10 to the minus 24 grams. Okay, so that's a simple conversion. And then if you divide both sides by that number, so if you just invert this number and then take a look at it, there it is. It's 6.022140776, the exact same number we started with. 1 gram is equal to that Avogadro's number of AMU. Okay, so there's an Avogadro's number of AMU in a gram. There's also that Avogadro's number of particles in a mole. So then when you're looking at, say, an atomic weight for glucose, you're saying, okay, how do I get to grams per mole from perhaps a mass we get off the periodic table of 180.2 AMU? That's the mass of one molecule of C6H12O6. Then what we might do is say, okay, you have an Avogadro's number, molecules of C6H12O6, and 1 mole of that substance. And then you also have that same number, 6.022, times 10 to the 23 AMU in 1 gram. So that Avogadro's number cancels. The AMU cancels. The molecule cancels. The only things that don't cancel here, grams per mole. So this works out to be 180.2 grams per mole. So this is just one last, we've shown this in the last video, we showed it in class. This is just how we get this synonymous scale with the AMU per particle is the same number as the grams per mole for a given compound or a given substance. So we can convert quantities from grams to moles to formula units, grams to moles using the molar mass. So if you have 5 grams of glucose, all you got to use is the grams per mole, the molar mass, to convert to moles of glucose. You can then use Avogadro's number to go to the formula unit. The formula unit for a molecular compound is molecules. So you could go from grams to moles to molecules for this substance. It's going to be a big number. You can also then go to atoms. You could say how many H atoms are there? There's 12 H atoms for every one C6H12O6 molecule. So you're just using the formula and the subscripts to figure out that quantity. So how many moles of water are present in a sample that contains 3.0 times 10 to the 24 H atoms? So the number of moles of water is what we're looking for. Start with 3.0 times 10 to the 24 H atoms times there's 2 H atoms for every 1 molecule of water. There's an Avogadro's number of water molecules in a mole of water. So we've gone from H atoms to molecules of water, 2 H atoms per 1 molecule, and then Avogadro's number of water molecules in a mole. Okay, so go 3.0 times 10 to the 24, divide by 2, divide by 6.022 times 10 to the 23. That works out to 2.5 moles. So how many moles of water are present in a sample that contains 3.0 times 10 to the 24 H atoms? The answer is about 2.5 moles of water. So 2.5 moles of water contains 3.0 times 10 to the 24 H atoms. Okay, so let's look at a practice exercise here. Which of the following samples contains the fewest sodium atoms? If I have a mole of sodium oxide, 45 grams of NaF, 50 grams of NaCl, and then 1 mole of NaNO3. Okay, so if I have a mole, so this is a tricky question in a way just to look at the answer. Something we might have to think about this. So we have a mole of sodium oxide, we're going to have 2 moles of sodium present. If I have a mole of sodium nitrate, I'm only going to have 1 mole of sodium present. If I have 50 grams of sodium chloride, that's 23 plus 35.45. So that's, in terms of the atomic weight, that's less than a mole. So that's less than 1 mole of sodium present. Because I have less than a mole of sodium chloride, there's only 1 sodium per NaCl. And fluorine's mass is 19 plus 23 for sodium, so that's 2. That's about 42, so that's slightly more than a mole, but definitely not 2 moles of sodium fluoride. So this is slightly more than 1 mole of Na, but it's less than 2 moles of Na. So the fewest moles of sodium chloride is going to be answer C, the 50 grams of sodium chloride. Weird question, involves some naming, but it really involves thinking of formulas. How many moles of sodium do we have present? Do we have a mole? Do we have 2 moles? Do we have less than a mole or more than a mole? So C works out to be less than 1 mole of sodium. Okay, so I'll provide some solutions for the remaining examples here in a second part to this video later. Thanks for the attention.